All right, thank you very much. So I want to make sure that everybody in the room is on board and understands what ultra high performance concrete is, and discuss how it differs from traditional concrete a bit, and then I'll talk a little bit about some of the innovative things that we're doing with nanotechnology. So ultra high performance concrete is ultra, as we like to talk about, right? It's ultra strong in compression, which is kind of a byproduct of what we're going for. We're going for ultra high tension or tensile strengths. That's what we're looking for. Traditionally, with ultra high performance concrete, you're going to get tensile strengths of around 1,000 to 1,500 psi. And there's a new test that was developed. Some of you are familiar with the old dog bone direct tension test. There's a new test that's been developed that makes it a little bit easier on the labs. You don't have to necessarily buy the expensive grappling equipment to hold those dog bones. AASHTO T397 has been developed for testing and direct tension. It's ultra dense, right? It's we have great impermeability of this product, and unlike normal concrete, it's not going to fail at your first crack. So you're getting ductility out of the product, and we'll talk about that in greater detail. So the other things that make a UHPC special is its abrasion resistance. It's very, very tough. It has very good bond strengths, which are going to help in some of our applications. I'll get into a little bit here, especially with infrastructure. We're going to talk about where that ultra high bond strength comes into play. It has great energy dissipation, and as a person who was hit directly by Ian and Cape Coral, I'll tell you it's great for resilience. Any concrete is that way, and of course UHPC enhances that beyond our normal capabilities. And of course it's very good for blast resistance, these kind of things, because of that ability to dissipate energy. So there's a lot of engineers in the room, and you folks are smarter than me at this, but I'm going to give you the basics. So the tensile properties of UHPC are really what sets it apart. And the strain behavior is key to that. So in a traditional concrete, you're going to get a response to a load where it'll take the load, you'll hit a first crack, and then your load will drop off. That's demonstrated in both of these examples. The difference with a fiber reinforced concrete is you're going to get a softening, you get strain softening. So what will happen is, this is an example of standard like GFRC or other fiber reinforced concrete. And what will happen is you'll achieve a crack will occur, and then you're getting a softening. So instead of a brittle failure, immediate brittle failure, it's a slower failure. And so you're getting a softening branch to that, and that's demonstrated here in this graph. With UHPC, you're going to get strain hardening first, and then delayed strain softening. So you're going to achieve your first crack here. You're going to continue to get additional load pick up by that item, and that UHPC will be able to resist that load. You're going to get more strain hardening, and then you'll get this delayed softening failure. So that's really what sets UHPC apart. And the reason that we're able to do that and get that delayed strain softening and that post-crack ductility is our fiber content. It's extremely high strength in compression. Remember, it has extremely high strengths, and then we have high fiber content. And that's what's going to give us this behavior. Fibers are key for that. This is an example. This is we did a test on some UHPC at 7 days, and you can see this is a real-life example. So we have fibers in our mix. This is with steel fiber. We get our initial cracks here about 1,000 psi, and then it peaks at about almost 1,300, 1,280, and then you get this delayed strain softening of a failure. So this is what UHPC is all about. This is what sets it apart. It's not brittle, and you get some ductility out of it. Like I talked about, fibers are key. So for UHPC, steel fibers and high strength fibers are going to give you that response that we're looking for, that strain hardening. And you're going to get, typically we're using a cold drawn high tensile strength steel fiber. These are examples of the fiber that are traditionally used. They're short, they're like a 0.2 millimeter in diameter. They're like little needles. And anyone who's worked with UHPC knows it's pretty stabby stuff. So as you hold it, you have to be careful that you don't get stuck with these little needles. But what's great about these, because they go into the mix and they go everywhere, you get this tremendous tensile behavior. You can also use for architectural applications in buildings and those kind of things where you can't have rust content and discoloration on the surface. We'll use non-metallic fibers. So these non-metallic fibers might be alkali-resistant glass or monofilament like PVA. These are POM fibers, which are another plastic, a monofilament plastic fiber. Once again, it's a short, very narrow fiber, 0.2 millimeter diameter fiber on this fiber. And you can also use carbon, you can use basalt, you can use like a mini bar, which is like a mini GFRP, and you get different performances depending on your fiber. So UHPCs, and there's lots of different ways you can approach these materials, but almost all of them have this that are the same, right? So they're a reactive powder system that depends on particle packing. So our largest aggregate size will typically be a sand, like a medium to coarse sand, on down to the nano scale. So we're just packing every single little spot within that matrix with material. And it's all the better when we're using reactive materials that contribute to that paste portion of our concrete, right? So we're typically going to have sand, Portland cement. These are Portland cement-based systems. A lot of times people will use silica fume and supplementary cementitious materials such as fly ash, slags, and then a lot of them will have a mineral filler such as a silica flour, which is a ground quartz material, or limestone powders. So, things like silica fume and silica flour have, potential health issues associated with them. However, they're widely used in these materials in UHPC mixes. So what's different about the nanotechnology and the innovation that ceEntek has come up with is it's a simple, stable, safe, and sustainable system. It's simple because we've eliminated a lot of those other materials. We don't have the silica fumes and the silica flour associated with some of those other materials. It's going to have basically a carbon nanofiber, cement, sand, plasticizers. We still have to reduce our waters, and then and water, and that's your system. Pretty simple. It's safer. You don't have to worry about some of the health effects of some of these materials, and then it has the same sustainable advantages of traditional UHPC, and then we've committed ourselves to be net zero by 2035. I'll talk a little bit more about that as well. So carbon nanofibers, I've talked to a lot of different people and they say, okay, great, I want your material, let's use it. Can I get rid of the fibers in my concrete? Because I have nanofibers now. Different scale. We're talking a completely different scale. These little 1/2 inch, 0.2 millimeter fibers are giant compared to the nanofibers that we have. Those fibers are 0.2 millimeter in diameter, which means that if you have a carbon nanofiber that's 1 nanometer, that you could line up side by side on the head of that fiber 200,000 fibers. It's tiny. These fibers go everywhere. And where they really are effective is in that ITZ, in that interstitial transition zone. Right up against the other fibers, right up against the sand, in that paste, coating everything, bonding to everything. That's what makes this stuff so good. And that's what really makes it powerful as far as the bond strengths. Is you have these tiny, tiny little fibers, they're up against all these other materials, and they go everywhere and they grab a hold of stuff, and they help hold things together. To try to give you a little bit of the scale, there are 5 quintillion nanofibers in a cubic yard of concrete. It's a big number. I can't wrap my head around it. There's 18 zeros behind a 5. That's how many fibers there are in a cubic yard of concrete. So this material goes everywhere. It's filling all those little tiny angular spaces down at the nanoscale, down at the very basic level of the material, and they're helping eliminate microcracks. So if you can eliminate your microcrack, which is going to be happening at that ITZ, then you're going to help delay and eliminate the macrocracks. So the idea is that you keep on holding that microcracking at bay, and that holds off the other ones. So when these materials get out there, they're going to improve the bond and they're going to make everything stronger. A lot of people have heard of the different nanotubes, which is a more complete structure that you've grown and you've been able to make. Nanofibers are more of a stacked cup orientation. It's a lot less complete. It's not nearly as a complete structure, so it wants to grab a hold of the material around it much better. And it's made of elemental carbon, right? So the nanofibers have this honeycomb stacked cup shape, which helps them grab everything. And the neat thing about this carbon is we're going to make it out of, currently we're making it out of the hydrocarbons, but we can also make it out of waste CO2. So if our raw material stream is waste CO2, you can see the sustainable advantages of that, right? We're able to capture CO2 and actually make a product out of it. So the way that these nanofibers are made is we're using a carbon vapor material. We're adding a catalyst in a reactor, and we're making our carbon nanofibers, which are dispersible in water, which is a real key. A lot of times if you try to do this, it's all going to clump together, and you're not going to be able to get that dispersion, so it isn't going to go everywhere. It just becomes a little clump. We don't want that. We want it to go everywhere. We add that in with superplasticizers and some additives, and that is supplied as the additive that you're going to put with that sand cement premix, and add water. Sometimes you can add accelerators and fibers, and now you have a UHPC. One of the great things about this is we've proven that you can use a waste stream, CO2, to make your carbon nanofibers. So once you capture CO2, you can use it to produce these carbon nanofibers, which is a huge advantage for sustainability. In a demonstration product that we've done, we were able to grow very good quality fibers, and we had good growth of those fibers. And this is the technology, this is the innovation that we're really excited about, because it does open that door to using waste streams of CO2. So that's what UHPC is. Where we use it are in these different applications. There's a lot of infrastructure work going on. The material can be used very well in buildings, and of course in precast applications, offshore wind tunnels, these kind of things, or wind towers, I should say. So in the United States and North America, the real driver of this has been the ABC, Accelerated Bridge Construction Program, which is a state-based program that identifies and deploys underutilized innovations. So the key is what we're trying to do is get highways open quicker, get projects done faster, and have less impact on our societies due to the construction. UHPC is a great match for this because it can be coupled with precast bridge elements, precast infrastructure elements, and it really accelerates that. So this is an example right here. This is traditional concrete. This is from a precast beam. This is the UHPC that's in the joint. Because the bond strengths are so very good, we're able to reduce the splice lengths on our steel. So instead of having a 25 or 30-inch joint, now I've closed my joint width down to maybe 6 or 8 inches. And I'm no longer the weak link in between my precast bridge elements. I'm now the strongest part. So I'm able to transfer the loads in between the different sections of the bridge And I'm able to do that very completely with great long-term durability. You're not going to have to worry about water egress and other problems associated with that joint, because this is now the strongest portion of that precast element. You can see here where you've got these very narrow joints in these bridge deck portions where we can drop these precast elements into place, use a UHPC closure pour, and now we've got essentially a finished bridge. So the other big advantage of this material, like we talked about, is the sustainability of it. We're trying to reduce our environmental impacts. Predominantly, we're doing this through the use phase, right? We're getting more durable materials. There's less material to get there. You don't have to be as massive. Remember, we've already reduced our joint, for instance, from 30 down to 8 inches. And then we're able to do this very quickly because we're able to utilize precast and other materials that get the job done quicker, right? And because there's less material, there's less mass, you have less transportation impacts, less truckloads go down the road, you have less impacts from that, emissions associated with that, and all the truck traffic, et cetera. Less embodied energy because you're so much smaller, less CO2 emissions, of course, associated with that. And then the key is that we design to take advantage of these strategies. This is a good example of what can be done. So there's a waffle slab design that we'd be glad to share with you and have you put on your bridges. You take these slabs, you put them into place. It's a precast element ready to go. You can put this either on steel or whatever kind of bridge beams you already have there. It's a great retrofit application. And you leave some pockets in here to where you're going to be filling in with UHPC. When you do your joints, you can do the pockets to tie it down to your existing girders or your brand new bridge beams that you put out. And you're going to have about half of the concrete, a lot less mass, obviously. And you're going to have roughly 60% less steel, right? Because you don't need as much rebar out there in your bridge deck because you're getting so much strength from your reinforcing fibers that are integral into the mix, right? This is an integral fiber reinforced concrete. So you don't need as much traditional steel out there on the deck. And then since it's so much less, it's a lot less weight. So once again, you can see the obvious advantages for sustainability. The other thing is it's going to last a long time, right? So in buildings, the big issue with not only infrastructure but also buildings is the maintenance. So if we can delay that maintenance, make materials last longer, that's a huge environmental benefit. So in buildings, it's typically used for very thin, intricate elements. So the idea is that you're going to use a thin shell. You're going to go, instead of having a 6-inch thick wall, maybe my wall is only 3/4 or 1 inch thick. So it's a much thinner, much more intricate patterns can be achieved with this. Because I'm not trying to lay down a steel mat ahead of time, I can go very intricate patterns. This is Hicon did this in Denmark. This is a university in Denmark that has over 60% voids in those rain screens. So imagine trying to do that with reinforcing steel, right? You're getting a rebar guy out there and say, hey, this is what we want you to build. You're not going to be able to do that. Now, they do use some reinforcing, typically like a GFRP, a glass fiber reinforced polymer, reinforcing bars. And they'll have those typically like at the corner's edge here where you have the most loads, right on where those big circles are coming in. But other than that, it's going to be intricately reinforced with the fibers. Same thing here. This is a very recent project in Qatar where you can see these very thin panels are put in place. And of course, some of them are perforated with windows, et cetera. So, very thin, very intricate patterns can be achieved with this. Perforated or solid rain screens, they can be very blast resistant, like we talked about. It's great for personnel protection, and of course it can be used in a structural element. The same thing you're building your bridges out of, you can do internally for your buildings as well, obviously. Here's some examples of some, very complex. It actually looks very simple, right? What could be simpler than these floating stairs hanging in your building, right, in your office building? But the idea is that the engineering behind it is they figured it out and said, okay, all I need to do is hang some aircraft cable and I can support this. Because this is so thin, my dead loads are less. And how many people can I fit on there? Maybe I put a couple pianos on there stacked up. It's going to resist all those loads. And it's going to have the tensile capacity to do that. Here's another example of something you can do is sandwich panels. So if you look at a traditional sandwich panel where you have, by that I mean a precast insulated panel with two whites on either side, right? So you've got concrete insulating, typically a rigid foam, and then you have concrete on the inside. That's a sandwich panel, right? So you can do if your traditional standard sandwich panel is going to be much larger, much thicker than a UHPC sandwich panel. With these next generation materials, you're going to be able to go very thin, and you're going to be able to get the same insulation value, but you don't have all that mass. So now I'm shipping, my square footage going down the road per truckload is 3 or 4 times as much because I don't have the weight restrictions. Right? I'm able to send a lot more material down the road. Every truck that you save is a lot of emissions that you're taking out of the equation, right? Like we talked about, the key is going to be that the materials, you have very efficient applications, and like we talked about, it's more resilient, it's going to last a long time, and of course, it's going to give you what you can, something that you really traditionally would be very difficult to achieve with concrete. So ceEntek is the first UHPC supplier who's committed to being carbon neutral by 2035, and we're working very hard to do that. And honestly, it's going to be about getting the material in place and designing for it. The idea you want to cut down your construction time, make sure you're going to utilize this in an application that's quick, that's going to solve your problems, and of course all these other benefits that you're getting from it. It's going to be lighter, it's going to be more durable. You're going to be able to do things with it that you couldn't achieve with traditional concrete. So with that, I'll be glad to take any questions that you guys have. Thank you very much.
Hey, so to recap, you keep the same UHPC mix, except that you do a better job of nano micro packing, the spaces and everything else through the nanocarbon fibers and also through the admixture that you provide. That's summing all up what I heard you say.
So the big difference is it's a little simpler. Instead of having a very long laundry list of ingredients in your UHPC mixture, then what ours is simpler, that we just eliminate all this. We basically compensate for being able to pull out the silica fume and the silica flour and some of these other materials. We compensate by having the carbon nanofibers. We're able to provide the performance without having those other materials in there. So similar to what you said, but it's a little bit, it's more of a, it's not, I would say it's not the same mix. It's the same basic components, cement and sand. I mean, those are in everything, but we eliminate a lot of those other materials.
But still, you're only working at the nano scale, right? You're eliminating the materials that we're doing the nano pack, the micro pack.
Yeah, it's actually, we've gone finer than those traditional, all these other materials. And so like you said, all of these materials are based on two things: particle packing and reactive powders. So the idea is that we're going to have a very reactive system. The materials are going to be able to form a cementitious paste, a Portland cement-based system, and then we've done the particle packing all the way down to the nanoscale. That is a key thing, absolutely. Thank you.
Thank you, Larry, for the excellent presentation. So I just had one simple doubt. So since you were using the carbon nanofibers dispersive superplasticizer, so I believe the superplasticizer particles would be like attaching to the carbon nanofibers in dispersing them. So does it mean that now the superplasticizer requirement for UHPC will be increased because a lot of superplasticizer particles will be involved in dispersing the nanofiber itself. So the amount of superplasticizer that you now need for the cement particles or the binders to disperse, that will like the requirement will be increased. So is it so?
So the neat thing about, and this is the innovation, this is where ceEntek has kind of cracked the code and done something different, is these carbon nanofibers are water dispersible. They don't necessarily need the admixture to make them disperse. They're water dispersible, and that is the key, because normally they want to agglomerate and form little clumps that are still tiny compared to anything else we can think of, but the idea is that these are water dispersible, and so they are going to go pretty much everywhere and so you don't necessarily need that superplasticizer load to go up. And I'm not going to say it doesn't go up at all, because I honestly don't know. That's beyond my pay grade to know that. But yeah, no. And this is something that I'm glad you brought up as a point, because UHPCs need high doses, relatively high doses, to achieve UHPC, because our water content is like 0.8%, or 8% of the entire volume, right? So our water cement ratio, we're used to water cement ratios. A good water cement ratio is around 0.42. That's what I always recommended when I sold cement. Use 0.42. We're 0.8. So it's tiny amount of water for our entire system. And then you just, if you knew how much cement was in there, which I can't tell you, then you'd still get an amazingly low water cement ratio. So the superplasticizers have to be there just to make the system work. And as far as I understand, and all the learning I have is that there's no appreciable uptick of the superplasticizer due to the carbon nanofibers, because they're water dispersible.
Larry, thank you very much.